Hello everyone. So this is a continuation of our watershed series. In the first part of this video, what we did was we compared two watersheds, Harave and Malayanapura, and we used some techniques, some approaches to actually show that we had some measurable effect of the interventions of the Reward and Sujala projects. Now in this video, as we continue the analysis, there was a small change in the direction of the analysis. So as the work progressed, I had discussion with Professor Shekhar Muddu and Professor Laurent, and we decided that instead of focusing on two watersheds simultaneously, why don't we actually focus on one watershed which has a clear period before intervention and after intervention. So it has clear pre-intervention period of 3 to 4 years, and after intervention we have 3 to 4 years, and it has no effect from neighboring watershed because it's the upstream watershed. And when we had two watersheds, we had like spillover effects, upstream downstream effects, and different periods there were interventions. So although we claimed that difference in difference approach can filter out these effects by using dummy variables, so you can go back to part 1 and check that. It's better to focus on Harave watershed for now and establish that intervention has clearly worked and by what amount, and then maybe in the next final part, maybe in part 5 or part 6 of this series, if it continues, we can return to Harave and Malayanapura comparisons again, a stronger context with more established intervention effect in Harave. And before I go deeper into Harave, there was some questions comment that actually appeared in part 1 of this video. So the main question was, did this intervention actually helped farmers? So I want to be honest here. So in this study, I did not directly visit farmers or collect any crop yield data. I'm sure there are other teams within projects that they are doing that. So from what we have, we cannot claim that intervention actually helped farmers because we don't have crop yield or crop production data. So what we observe from satellite is just the backscatter that is actually related to soil moisture, and what it tells us that the soil is appearing to hold more water than before, and that's all we can say from the satellite. We cannot really say what was the economic benefit to the farmers without any crop yield statistics or field surveys. That would be my answer to this question. That only thing that our analysis is on based on satellites, and that can only show us if the soil moisture storage has increased, and that is exactly why these watershed structures are designed. But whether it had an impact on farmers is actually beyond the scope of this video. So this is the Harave watershed, and you see that we are not including Malayanapura anymore, and so what you see here are the sampling locations. And if you have seen the part 1 of this series, where I have explained how did we do filtering and sampling process, these were not actually randomly selected, and we used some logic to select these to represent different soil classes and texture, and removed zones like irrigation, settlements, plantations, and so many things. So you can always go back to part 1 of the series to understand this. And so here is the timeline. So what we have is that under Sujala-III project, most of the constructions, mainly the trench and bunds and other soil water conservation structures, happened during 2018 and 19. And so this gives us actually a clear experimental setup. So we have a pre-intervention period of 2 years, a construction phase, and a post-intervention period starting from 2020. And we also had, like, 2022 was an extreme rainfall year, so we will not include this year for any analysis. So if we compare how the watershed behaved before intervention and after the intervention, and since we are only focusing on Harave, We also avoid complications like upstream, downstream spillover effects. So actually the entire analysis on Harave for the Sujala-III project that we did is based around a simple regression model that I'm showing here. So here actually we are trying to find a linear relationship between the satellite backscatter, which is the sigma, and few explanatory variables. So let's go on the left hand side. We have sigma naught, which is the radar backscatter that is measured by Sentinel-1. And now on the right hand side we go term by term. So first we have alpha, which is the intercept, which means that even when there is no rainfall, the soil is not like a sheet of glass. It's not dry. It has some baseline level of soil moisture. So that is what is this alpha. So it's not zero actually. It has some y-intercept, and alpha represents this baseline moisture level. So I keep on tell moisture or backscatter. Here in this analysis, when I say soil moisture, it means satellite backscatter and vice versa. Although it's not same, it's we can assume they are directly proportional. And the next term is the beta 1 times rain. So here rain is simply the monthly rainfall amount, cumulative monthly rainfall amount, and beta 1 tells us how strongly the soil moisture responds to our rainfall, or the satellite backscatter is related to the rainfall. So if beta 1 is large, it means that whenever there is rainfall is increasing, the satellite backscatter or the soil moisture is also increasing. And if beta 1 is small, it means soil moisture or the backscatter is weakly related to the rainfall. And now the important term here is the beta 2 times post. So what is this post? It's the dummy variable. So if you have seen the part 1 in difference, we had several dummy variables. Similarly here we have only one dummy variable. So the post dummy variable is actually activated to 1 after the post treatment period between 2020 and 2025. Before that it's 0, so that term doesn't affect the equation or the regression fitting. So it's essentially 0. So what beta 2 is capturing is whether the soil moisture, the baseline soil moisture, is shifting, or it's the level is shifted after the intervention. So if the soil is capturing more soil moisture after the intervention, that is what is captured in beta 2 here. So if beta 2 is positive number, it means that for the same rainfall condition, the watershed is holding more water after the intervention. So this is what is directly measuring the effect of the structures that was constructed in the Sujala-III project. And now we have one more term called beta 3 times rain times post. So this term is checking something that is different. It's actually asking whether the relationship between the rainfall and the soil moisture itself has changed after the intervention. Maybe the intervention changed the structure of soil or something. So the relation between rainfall and soil moisture itself changed, and it's not because of soil holding more water, but somehow something else changed. So for example, before intervention, rainfall may increase soil moisture in one way, but after intervention, maybe the same rainfall is producing a different response due to climate change or something else. So, for example, bunds might have changed the infiltration dynamics or runoff patterns or something. So this is what a rain cross post interaction term tests. So what if beta 3 is 0? It means that rainfall response is same even before intervention and after intervention. That's what we want. So if beta 3 is positive, then rainfall has become more effective at increasing the soil moisture. Maybe the transpiration has reduced or something else that we don't want. So to test whether bund has effect or not, we want a beta 2 to be positive and beta 3 to be effectively 0. And finally, we have epsilon t, that is the error term that includes all the variables that cannot explain whatever is considered. It explains the other variability like measurement noise and other environmental factors like that. So these are actually, we will assume that epsilon t is a random variable. And now physically, based on how trench or bund structure work, we will expect that these structures are designed to store more water, so they should not fundamentally change how soil responds to rainfall. So beta 2 should be positive, meaning that watershed stores more water after the intervention, and beta 3 should be 0 or close to 0, meaning that rainfall response does not change. So let's see, and this is the regression model that we are going to analyze for our Sujala-III dataset, and how see whether the intervention actually changed the moisture behavior by examining the beta 2 and beta 3 here. So beta 2 is the intercept shift, beta 3 is the slope change, and let's see in the next slide about this. When we actually fitted the regression that I showed in the previous slide, what we found was that beta 3 was essentially 0 and beta 2 was around 0.021. So what this means is that the way the soil reacts to rainfall has not changed. The soil is behaving the same way before and after intervention, and so the only change is from beta 2, or because of intervention the soil is having is storing more soil moisture. So here what we have is that we fit two regression lines. One regression line is fitted using pre-treatment data. The other one is fitted after the post-treatment data. And what we see here is that the post-treatment regression line is exactly parallel and is sitting above the pre-treatment line, and their slopes are almost identical. So actually, since these two lines are parallel, this is a very important scientific result, because beta 3 is 0. If you see the regression equation, the equation actually simplifies, and the rainfall coefficient beta 1 actually is the same before and after intervention. The way it reacts to rain, we have the same rainfall, and so when the slope is same, the regression line is becoming parallel. The parallel structure also is another way to tell beta 3 is 0, or the rainfall is affecting soil moisture in the same way as before the intervention, but the entire system has shifted upward. That means that watershed is holding more water for the same rainfall. That's what we can see here. We can also quantify this shift through beta 2, and for different rainfall inputs, the increase in backscatter value before and after intervention ranges roughly from 16 to 20%, while the World Bank target was around 10%. So the analysis shows that we are exceeding World Bank target rate. So on average, it's 18% higher than what it used to be before intervention for 150 millimeter of monthly rainfall, which is the typical monsoon rainfall value. That's what we show here in the red box. So we see that the regression relationship has shifted upward and the soil is storing more water, and this is what we would expect after constructing these trenches and bunds, which are exactly designed for this, to slow runoff and increase infiltration. That is what is showing up in the backscatter here. But this figure is actually showing the average rainfall and soil moisture relationship. But one would ask if this effect is actually persisting over time. For example, once the bunds are constructed, does this increase in soil moisture remain stable? Because it may, or does it decline? Since we have few years after intervention, we could easily check that if the improvement that we are seeing is actually holding after we finished the bund construction. So now in this figure, I'm showing something called as soil moisture anomaly relative to the baseline behavior. So what do I mean by that? So let me explain briefly how we define this anomaly. So before we introduce the full regression model, right, that relates the backscatter soil moisture to the rainfall and intervention. So backscatter was related to the rainfall and the intervention and so many terms there, beta 2, beta 1 and beta 3. Now let's consider the baseline period, which means it is before intervention. During this time, the post dummy variable is 0 because the watershed structures are not yet built. So the equation naturally simplifies to a very simple relationship between rainfall and the backscatter. So in other words, it's telling us that for the given amount of rainfall, how much the backscatter or the soil moisture we normally expect in this watershed. So using this baseline relationship, we can now make a prediction. So for each month after the intervention, we calculate the soil moisture that would be expected based only on the rainfall, and then we compare this predicted value with the actual satellite measurement. Right? We fit a model before intervention, a regression model, and then using the same model we are predicting the backscatter and see and comparing it with the actual satellite backscatter. The difference is what we call as the residual here. If the residual is positive, what it means that watershed is holding more water, and that's why it's giving its the satellite backscatter is higher than what is expected. So finally we convert that difference into the percentage anomaly relative to this baseline. So when we say anomaly is 20%, it means that the soil is holding 20% more soil moisture, or exactly it's like 20%, it's reflecting more satellite signal, or the backscatter has increased 20% than the expected one from the rainfall alone. So if it was only rainfall, it's not explainable by rainfall, so the increase. So if we plot this anomaly year by year, we see this figure. The anomaly is positive and is actually increasing gradually. In 2020 it's 16%, and then it's 27% in 2024. So this is important because the rainfall has already been taken care in the baseline model, and this anomaly uh, is not explained by the rainfall. So it shows that the watershed is holding more water and is not related to rainfall but something else, and we expect that it is due to the trench construction. So this anomaly is another way of visualizing the same effect that we discussed earlier in our regression model through the beta 2 term. And now someone might ask why the anomaly is increasing uh, like after 2023. 2022 was a flood year, but this is not due to that because the rainfall has already been taken care by the baseline regression model. Maybe the flood is not captured in the linear relation. That might be one reason. Or the other possibility is that why we see the increase in the anomaly percentage after 2023 is because maybe the watershed structures take some time to fully stabilize and begin operating efficiently. So the storage effect may gradually become stronger as opposed to what we expect that it did decay and decline. Maybe it's strengthening. We do not know that. Another possibility is that the runoff is slowed, or maybe more water is infiltrating. All the flood water has infiltrated, and that's why we see consistently higher anomaly percentages here. But whatever it is the reason, the key point here is that the anomaly is consistently positive across all post-intervention years, which is suggesting that watershed intervention had some impact on the soil's ability to retain more water. Here actually we only consider in this figure the months from January to April, which are the driest months in the region. And the reason we do is to remove the direct influence of rainfall. So during this period actually there is no rainfall, and so the soil moisture we observe is mainly reflects how long the soil can retain the water that was actually stored earlier during the monsoon. So what we see here is that in both cases the soil moisture, that is post and pre-treatment, in both cases we see a soil moisture is gradually decreasing during the dry season, which is expected because of evaporation and root water uptake, transpiration, and so many things. But the important point is that the post-treatment curve remains above the baseline curve. So this means that even after several months after the rainfall has stopped, the soil is able to store more water than before the intervention. This is what this figure is showing us. And we also modeled the drying behavior using an exponential decay curve, and from that you can get what is the decay rate. So before intervention the half-life was around 11,000 days, and after the intervention it increases to 2,700 days. What it suggests is that the watershed structures are not only capturing the rainfall, but they are also able to retain the water during the dry period. And in this figure actually we separated the data by 4 major soil classes that was present in the watershed: clay, sandy loam, and loamy sand. And for each soil class we estimated the moisture increases relative to the baseline using the same analysis, the same regression, rainfall controlled model. So what we see is that all the 4 soil classes showed similar improvement around the range of 20%. One might ask if the intervention is helping certain soil type, or if certain soil type is getting more benefits. But from the data what we can say is that it's not related to any particular soil type. It's improving storage across entire landscape. So to summarize, what we have seen is that the rainfall soil moisture relationship is in fact shifting upward after the intervention, and we can clearly say that watershed is consistently wetter than expected. The Sujala-III watershed intervention has improved the soil moisture as per the analysis that we did on Sentinel-1. In the next part of this series we will compare with other type of data. So we have SMAP soil moisture data that has been downscaled to 400 meter. So we will do some analysis on whether SMAP data also shows this kind of improvement, and we can see what to do for part 3. Thank you for watching, and see you in the another part of this video.